Howdy. This is another video on Bronsted-Lowry theory of acids and bases and conjugate acid-base pairs. It's important because all buffers and indicators are composed of conjugate acid-base pairs. If you know the Ka of an acid, you can calculate the Kb of its base, its conjugate base. If you know the Kb of the base, you can calculate the Ka of its conjugate acid. The stronger an acid, the weaker its conjugate base. The stronger a base, the weaker its conjugate acid. So after watching this video, you should be able to determine if a compound is behaving like an acid or a base, identify the conjugate bases of acids and conjugate acids of bases. Given the Ka of an acid, you should be able to calculate the Kb of the conjugate base. Given the Kb of the base, you should be able to calculate the Ka of the conjugate acid. You should be able to determine if a compound is a strong acid, weak acid, strong base, or weak base, or neutral, based in part on conjugate relationships. And so the only difference between acid and conjugate base is the hydrogen ion. And so you can go from the acid to the conjugate base by just removing the hydrogen ion. Now notice that, so we have two hydrogens here, now we have one, so we removed a hydrogen ion. We have charge neutral, and we have a -1, so we also have to worry about that charge. Now if you want to go from the base to the conjugate acid, we add the hydrogen ion. So here we have SO4 2-, add a hydrogen ion, so we add an extra hydrogen, and our charge went from 2- to 1-. Whether a compound acts like an acid or a base depends on what it is reacting with. And so that's according to the Bronsted-Lowry theory of acids and bases. And so for all conjugate acid-base pairs, Ka of acid times Kb of the base is equal to Kw, and Kw is the autoionization of water. Now this is important because the stronger the base, the weaker its conjugate acid. The stronger the acid, the weaker its conjugate base. And so we can make a table of acidic, basic, and neutral cations and anions, and most of this table is based on conjugate relationships. And so conjugate acids of weak bases are acidic, conjugate bases of weak acids are basic. Now this one's a little confusing. Conjugate bases of strong acids are neutral. And so chloride ions, bromide ions, iodine ions, nitrate ions, and perchlorate ions are all neutral. And so we call them conjugate bases because we've taken acid and removed the hydrogen ion, but they are neutral. A little confusing. Now we got a couple more to this table, and so small highly charged metal ions are acidic. Alkali metal and alkaline earth ions are neutral. Hydrogen sulfate and dihydrogen phosphate are acidic. And so it's kind of cool. By using this table, we can actually determine if a solution should be acidic, basic, or neutral. And so a question you can see is sodium chloride acidic, basic, or neutral? And if we think about sodium chloride, it looks like an ionic solid, but it's aqueous, and so that means it's present as ions. Now sodium is the alkali metal ion, and so that's going to be neutral. Chloride ion is the conjugate base of a strong acid, so that one's going to be neutral. And so both of the ions are neutral, so that means sodium chloride aqueous is going to be neutral. You can look at another one. So potassium fluoride aqueous. So again, that looks like an ionic solid, but it's aqueous. And so that means that's present as ions. Now again, potassium ions are alkali metal ions. And so that's going to make that neutral. Fluoride ions, that's the conjugate base of a weak acid. And so fluoride ions are actually basic. And then, so that means that a solution of Kf should be basic. And so you'll be asked questions where both of these are neutral. When one is basic, the other is neutral, or one's acidic, the other is neutral. You'll never be asked where one is acidic and one is basic. And finally, we have ammonium chloride. And again, is it acidic, basic, or neutral? And it looks like ionic solid, but it's aqueous, so it's going to be present as ions. And so if you have a solution of 1 molar ammonium chloride aqueous, you have 1 molar ammonium ions and 1 molar chloride ions. And so ammonium ions, that's the conjugate acid of a weak base, so that's going to be acidic. The chloride ions, again, conjugate base of strong acid, so that's neutral. And so that means ammonium chloride solution would be acidic. Now we can take this a step further and go, okay, so what would be the pH of a 0.01 molar solution of ammonium chloride? We already figured out that it's acidic and that the chloride ions are not going to matter, right? Chloride ions will not affect the pH because it's a conjugate base of a strong acid. And so all we have to really worry about is the ammonium ions. Okay, so again, here we got ammonium chloride. We saw chloride ions are neutral, And so we're just going to forget about them and just focus on the ammonium ions, which you determined was acidic. Now the Ekman constant, the Ka for the ammonium ions, is not given in our table. Now again, Ka times Kb equals Kw, and so that means Ka is equal to Kw over Kb, and so this is how we can actually figure out the Ka for the ammonium ions. Now whenever we're doing equilibrium, we'll make a table. So initially we have 0.01 molar of the ammonium ion, 0 hydrogen ion, 0 ammonia, and so when X of this reacts, we'll get X of that and X of that. Equilibrium is initial plus the change, that gives us 0.01 minus X, X, and X. Now our K is really small, and again we determine this by Kw over Kb, and so it's 5.56 times 10th, and again K is products over reactants, and so if your K is really, really small, it means you're going to have mostly reactants, and so most likely X is negligible compared to 0.01. And so we have our approximations. Now we can write down an expression, products over reactants, coefficients become exponents. And so at equilibrium, we should have X and X for the hydrogen ion and ammonium ion. And we have 0.01 for the ammonia, and then 0.01 for the ammonium ion. And now, so X squared over 0.01 equals that. We can solve for X and we get 2.36 times 10 minus 6. Now our approximation was good. That is a lot smaller than 0.01. And so at equilibrium, we'll have 2.36 times 10 minus 6 hydrogen concentration and 2.36 times 10 minus 6 ammonia concentration. Now we're asked about the pH, and so the pH is equal to minus log of the hydrogen concentration. And so minus log of 2.36 times 10 minus 6 is equal to 5.63. And so we should assume that's going to be a little bit acidic because this is a weak acid, and it is a little acidic. Remember, at room temperature, acidic would be pH lower than 7. A little confusing that the lower the pH, the more acidic. We could also ask, what is the Ekman constant for the following reaction? And so we have ammonia plus HF going to the ammonium ion plus F minus. And the question is, how can we come up with a series of reactions with Ekman constants that we know, and then add those reactions to get this reaction? Remember, if you add reactions, you multiply the corresponding equilibrium constant. Well, we notice that HF is a weak acid, and the ammonium ion we just saw was also acidic. And so we can think about those two reactions. So HF going to hydrogen ion plus fluoride ion, that's the Ekman constant there is the Ka of HF. Now ammonium ion going to hydrogen ion plus ammonia, we flipped it, and so that's going to be 1 over Ka. Now if we add these two reactions, we'll get that reaction, right? The hydrogen ions will cancel, and so we'll be left with ammonia plus HF going to the ammonium ion plus F minus. Adding these reactions, we multiply the Ekman constants. And so the Ekman constant of this reaction that we're looking for was Ka of HF divided by Ka of the ammonium ion. So that's pretty cool. We're actually able to determine the Ekman constant for that reaction. Now, we did it in terms of Kas. We can also try it in terms of Kbs, right? Ammonia is a base, and so ammonia plus water goes to the ammonium ion plus hydroxide. Ekman constant for that reaction is Kb of ammonia. Fluoride minus ion is a weak base, plus water gives us HF plus hydroxide ion. And so this one's written backwards, so that's 1 over Kb. Now if we add these two reactions, the waters will cancel, the hydroxide ions will cancel, and we'll be left with ammonia plus HF goes to the ammonium ion plus F minus. And so then if we multiply these two Ekman constants, we have Kb and 1 over Kb, we get Kb of ammonia divided by Kb of F minus. Kind of cool. So we could actually determine the Ekman constant for this one by looking at the Kas or by looking at the Kbs. And so the Ekman constant for this reaction is equal to Ka of HF divided by Ka of ammonium ion. And it's also equal to Kb of ammonia divided by Kb of F minus. Now it's kind of interesting. If we look at it, the K for this reaction would be greater than 1 if HF is a stronger acid than the ammonium ion. It'll also be greater than 1 if ammonia is a stronger acid than F minus. So notice that ammonia and HF are on the same side. And so the stronger acid is always on the same side as the stronger base. And so the stronger acid between ammonia and F minus. Ammonia is the stronger base. And HF is a stronger acid than the ammonium ion. Now, stronger means more reactive. And so this stuff on the reactants are more reactive than the products. And so that means at equilibrium we'll have mostly products. And so our K is greater than 1. Now, it's also kind of interesting if we look at it. The conjugate base of HF has to be weaker base than the conjugate base of ammonia. Hence, ammonia is a stronger base than F minus. And so again, for this type of reaction, the stronger acid is always on the same side as the stronger base because of conjugate relationships. And again, stronger acid means more reactive, less stable. And so if your stronger acid is reactant, then you'll have mostly products and your K will be greater than 1. Now, if you know the stronger acid or the stronger base, you're fine because remember the stronger acid and the stronger base are always on the same side. And so this is a really cool way you can actually determine if the Eckram constant for reaction should be greater than 1 or less than 1. So if we look at this one, is the Eckram constant for this reaction greater than 1 or less than 1? And so we have the ammonium ion plus chloride ion gives us ammonia plus HCl. Well, this is pretty easy. HCl is a strong acid, so this stuff should be stronger. So we should have mostly reactants at equilibrium, and so our K should be less than 1. You could also go with the bases. Chloride ion is a conjugate base of HCl. It's neutral because HCl is a strong base, and so ammonia is going to be a stronger base than Cl minus. So it's nice if you can know both the stronger acid and stronger base, but if you know either the stronger acid or the stronger base, you can still answer the question. So here we have ammonium ion plus hydroxide going to ammonia plus water. And so ammonia and hydroxide are bases. So hydroxide is going to be a stronger base. Ammonium ion and water are acids. The ammonium ion is going to be the stronger acid. And so the stronger acid, stronger base is reactant. And so at equilibrium, we should have mostly product. And so our K should be greater than 1. And so it's really kind of cool. We can also look at a table of acids and Kas. And so the stronger acid goes up. These are the conjugate bases. The stronger base goes down. Of the following, which can HF react with for K greater than 1? And so here we have HF. And so HF is an acid. It can react with a base. Which one of these bases will it react with to produce a reaction as a K greater than 1? And so the stronger the base, the weaker the acid. And so the stronger base, the stronger the acid, that will give us a larger Eckram constant. And so if HF reacts with any of these 4 bottom bases, that will give you a K that is greater than 1. And so conjugate relationships are really important. Ka times Kb equals Kw. The stronger the acid, the weaker the base. The stronger the base, the weaker the conjugate acid. It enables us to build this table and get the blue part. And so using this table, it can actually determine if a solution is going to be acidic, basic, or neutral. Using conjugate relationships, we can also determine Eckram constants for reactions. I hope that helps.